All right, so today we're doing special systems. We're going to classify our linear systems. So all of our systems can be classified as consistent independent, consistent dependent, or inconsistent. So it's just a classification system today that we're talking about. And we want to recognize the relationships between the slopes and the y-intercepts within the linear system. All right, so we've got this awesome chart and some definitions up here to look at to get us through that. So first of all, the inconsistent system would be this one right here. I have no idea what's going on with my board. All right, so there is no solution because we have what? What do you see here in this graph? They're parallel, okay? So they're parallel lines, which means their slopes are the same, but their y-intercepts are not, okay? Or if we do substitution or elimination, the results from when we do those are going to give us a false statement. We're going to get something like 0 equals -2 or 6 equals 12, something that's false. And if that happens, we know that it is inconsistent. Oh my goodness. I was like, I don't know. Right. It didn't do this last hour. Well, it started to, but then it didn't. Okay, we'll see. All right. Then we have, I don't know. Maybe if I put the pen down, maybe it's the pen. We'll see. I know, right? Okay, so then we have a consistent system. So we've got two of those. Consistent here and consistent here. Okay, not so much. Yeah, right? Okay, so we have two consistent systems, one here and one here. So these have one or more ordered pair solutions. Okay, which we've talked about those. An independent consistent has only one solution. Okay, so that's this section right here. Okay, they say consistent independent, it's the same thing as independent consistent. You can call it either one. Okay, but if it's independent, it has one ordered pair, only one solution. A dependent consistent, if I could get this one, or a consistent dependent, this is when we have the exact same line. So all the points on a line, it has an infinite number. That's when what does our solution look like in that case? Not no solution. That was parallel.
All solutions.
How is it all solutions? We didn't write all solutions. It's a true statement. We write the equation, right? This is so you might make yourself a note that we write the equation, okay, there for this one, okay. But yes, that's when the equation is the same. So we're going to see all three types of these today. But again, we're talking about just classifying them and what's the name of these systems. So let's look at example 1. We'll do 1A first. It says solve the system. Then down here at the bottom, it says solution and system type. So that's it. We're just going to solve it and then put it in a category today. How do we want to solve this one? We could cancel. Okay, so that would be elimination, right? These would cancel. That's okay, you're good. If you see they cancel, that's the way we're going to do it. So elimination. So it would be x plus x.
2x.
Okay, good. Okay, so here's our x. Then we want to plug it back in.
Does it matter which one?
Nope, in elimination it does not. So we can do 6 plus y equals 5. Subtract 6, y equals -1. All right, so my solution is what? 6, -1. And what system type is this? If it has an ordered pair for a solution. Consistent. Yep. Whichever way you want to write it. So consistent, independent. Should have made that line a little longer. How about B? How would you guys like to solve B? You could get y over, but remember, like I put this one on there on purpose. Don't forget we also have substitution. This one's already solved for x, right? So we already know our x, and we can put it in there. So we could have 3 times negative y plus 2 plus 3y equals 6. Do you remember that? Okay, so the substitution. So negative 3y plus 6 plus 3y equals 6, because we distributed. You should like where this one's going. Okay, so if we look at this, right, combining like terms, we kind of talked about this from the homework. We have a negative 3y plus a 3y. Those just cancel, right, when we combine them. So then we have 6 equals 6. Yeah. What kind of system is that? It's consistent dependent, because this is a true statement, right? 6 does equal 6, so we've got a true statement when we did substitution or elimination. So the system is consistent dependent. Nope. The solution is an equation. We need to write the equation in slope-intercept form. How are we going to write this equation in slope-intercept form?
Add the y.
Okay, so I'm going to take, well, because they're both, but because it's consistent dependent, it's the same line, right? Okay, so we can take either of the equations. So if we take the first one, x equals negative y plus 2, we want to put it in slope-intercept form. So we could add the y. So then we're going to have x plus y equals 2. There could be. Then we would have, but it still would have been the same number of steps because we had a negative y. So it doesn't really matter. You're okay. So now how do we get it? We're not quite in slope-intercept form. Minus x. All right, so that is what we put, that's our solution. Y equals negative x plus 2. Good. So like I said, when you, on your table, you might want to put where it's, you know, like it's your type of system, we maybe should add like what the solution looks like. So an ordered pair, then we're going to have y equals mx plus b, and then for no solution, we got no solution. Okay? Or maybe make that up there in your number of solutions. Fantastic. You guys doing okay so far? Any questions? Everybody have a copy down? Almost? Okay, I'll give you a second. I'll hydrate while you copy. Good. That was perfect timing. All right. So then example 2 looks a little different. Which equations form a consistent dependent system and which form an inconsistent system? So this time we have 3 equations and we have to pick out the ones that make each of these. So it says, there's a little hint here. It says write each equation in slope-intercept form so you can compare their slopes and their y-intercepts. Okay? Because in order to know, okay, there's a lot of information on that table on the front, okay, about their slope and their y-intercept. So instead of solving all of the systems, because we could make a system with 1 and 2, or 1 and 3, and 2 and 3. Do you want to solve all those systems? No, right? Because that's, you're doing elimination 3 times. You're doing like then plugging it back in to find each of those. So maybe we don't want to do those each time. So the easiest way to do these is actually to put them in slope-intercept form. Okay, so let's check that out. So for equation 1, I'm going to circle the one there. It's close to slope-intercept form. Divide by 3. Good. So y equals, remember this is one of those places where you guys trip up. What's negative 3 divided by 3? Negative x. Okay, don't forget, then you have to do 9 divided by 3 is, okay, so positive 3. So here's my slope-intercept form for equation 1. All right, equation 2. X plus y equals 4. Ooh, Okay. So y equals,
Y equals 4 minus x.
no, it has to be, the x always comes first. Okay. Negative x plus 4. Good. All right, so what can you tell about equation 1 and equation 2 right now?
They're consistent.
What do you mean they're consistent?
They're true statements. Are they?
We don't, no, just what can you tell about them from this? From their equations, what, don't even give me anything about their system. What can you tell about their equations? They what? Well, they're both in slope-intercept form. We could graph both of them. I'm not asking for any of that. Just look at this equation. Y equals negative x plus 3. Y equals negative x plus 4.
They're parallel. They're going up by 1.
Okay. What's going up by 1? Okay. Why are they parallel?
Because they have the same slope.
Okay, that's what I'm asking you for. Like, you know, this is y equals the slope times x plus the y-intercept. They have the same slope. Okay, so we have the same slope, or the same m, which means that they're parallel. Okay, those are conclusions we can draw just from the equation. What else do we know from the equation? What do you know about linear equations? Connor, you said so they're going up by 1. What are you talking about they're going up by 1? Anybody have any idea what he's talking about? They're going up by 1? The b, the slope-intercept, okay, has a difference of 1. It's not going up by 1, but it's a difference of 1. So then the y-intercept, or the b, right, are they the same or not the same?
Yes.
Well, are the b's the same? Is the y-intercept? Okay, so then we know b is not the same. Those are the two things we know. They have the same slope, so they're parallel, but they do not have the same intercept. So are they the same line? No, they're not the same line. Okay, perfect. Let's do equation 3 then. Get it in slope-intercept form. So we've got negative 6x equals 6y minus 24.
Add 24.
Okay, we can add 24 to both sides. So we'll have negative 6x plus 24 equals 6y. Divide by 6. All right, so this is the same as what we talked about on equation 1, right? What's negative 6x divided by 6? Negative x. And what's 24 divided by 6?
4.
Okay, so then we have plus 4 equals y. Again, for some people this is hard. We can flip the left and the right. So we can say y equals negative x plus 4 to get it in the y equals mx plus b. Okay, so 2 and 3 are the exact same equation, right? So same equation. There should be an e in there. Okay, so these are the exact same equation. Perfect. What about 1 and 3?
No.
They're not the same, but does this stuff apply to it? The same slope? Yeah, this also applies to that one, so 1 and 3. All right, so I'm going to leave that there. I'm going to move this up then. Now that we know all that, which equations are going to form a consistent dependent system? Look back. What is a consistent dependent system? They're the same. So 2 and 3? Okay, so we're going to write 2, which was the x plus y equals 4, and 3, which was the negative 6x plus, equals, pardon me. I hit the wrong one. Equals 6y minus 24. Any others make consistent dependent systems? No, that's it. So which ones would make an inconsistent system? Okay, so 1 and 2. And so 1 is the 3y equals negative 3x plus 9, and 2 was the x plus y equals 4. And 1 and 3. Awesome. Now, I do want to show you, you've got some room at the bottom there, just what a false statement looks like. So which of these, when we put them together, is going to give us a false statement? Which one gives us a false statement? 1 and 3. Either of these inconsistent systems is going to give us a false statement when we solve it. Okay? Doesn't matter which one. So I just wanted to, like, if we look at it, okay, we can, I want you to see what the false statement is, like what it looks like. So you're not like, why we haven't done this? So we can just even take the equations from right here. Okay? So we could do, right, 1 and 2 or 1 and 3. So these two are, I say, or we could do this one. It doesn't matter. They're all the same. So if we put those together, so y equals negative x plus 3 and y equals negative x plus 4. Okay? And we wanted to use substitution or elimination to solve it. Again, I just want you to see. I might take this one and multiply it by negative 1. So then I would have negative y equals a positive x minus 3. We okay with that? The y's cancel, the x's cancel. When the y's cancel, what number is that? 0. There's nothing else on that side of the equal sign. Okay, so it's a 0. And then 4 minus 3 is 1. So this was our answer. Is that true? No, it's false. So because it's false, we have just proved again that it's inconsistent because it's false. But that's what you're going to get something like this. And you're going to be like, wait a minute, this looks stupid. This is not right. I must have done something wrong. You didn't. It's just a false statement. All right, then you can get started on your homework. You get 5 of your homework problems done.